Hi, and welcome to a friendly introduction to deep learning. My name is Luis Serrano, and this is me, and I work at Udacity. So let's start with a question. What is machine learning? This is the question we're going to answer now. So let's start with an example. We have a human and we have a cake, and our goal is to tell the human to get the cake. So we can do this very easily with one instruction: go get the cake. Then the human realizes what to do. She goes and gets the cake. Let's go. Let's say we have the same problem, but now we want to solve it with a robot. So for a robot, it's not that easy. We can't just say go get the cake, right? We have to give it a full set of instructions. So first instruction, turn right, then go 10 steps, turn left, then go 4 steps, and then get the cake. So that's an okay solution, but first of all, it's a little complicated, and second of all, it's not general. If the robot is like in a different position, if it's here, then we need a completely different set of instructions, right? Turn right, go 3 steps, turn left, go 5 steps, grab cake. So we want a solution that is general. We want to, like we did with the human, we want to take one instruction and give it to the computer, and no matter what the location of the computer, we want to find the cake. So this is what we do. We're going to say, calculate the distance to the cake. So the robot calculates it, and it's 5. Then we're going to tell the robot to move around itself and pick a direction where the distance decreases. So the robot goes here, looks at the distance is 4.5, then tries a different direction. Now it's 5.3, tries a different direction. It's 5.8, so it realizes that the best thing it could do was to move right. So it takes a step in that direction. This is the 4.5. And then the next instruction is repeat what you just did until you find the cake. So the computer is going to look around itself, keep finding the direction that minimizes the distance the most, and gets to the cake. And this is in a nutshell what machine learning is. Let's look at another example that's maybe a little more complicated. We are on top of a mountain. It's called Mount Everest, and we don't know how we got there, but we know that we want to descend the mountain. But it's also very foggy, so we can only see around us. We can't really see the whole mountain. So what do? Well, we look at our surroundings and we try to figure out in which direction we can descend the most. So it's this one. So we take a step in that direction. Then again, we look at our surroundings, look at what direction we can descend the most, take a step in that direction, and then do it again. Look at our surroundings, where do we descend the most, take a step in that direction, until we successfully descend the mountain. This algorithm is called gradient descent, and if you like math, what we really did was we looked around us, we took the derivative or the gradient of our height function, and then the gradient pointed at the direction where we decrease the most, and then we take a step in that direction. In the previous cake example, we took the derivative of our distance to the cake, and that points to the direction that we decrease the distance the most, and we keep doing. That's why it's called gradient descent. So let's look at the problems that we just solved. First problem was get the cake, and the second problem was descend from a mountain. Then let's just think of any machine learning problem, which is solve any problem. What we're trying, how did we solve the cake problem? We minimize the distance to the cake. How do we solve the mountain problem? We minimize the height. So in order to solve any machine learning problem, what we want to do is we want to find a metric that tells us how far we are from the solution, just like how far we're from the cake or how far we are from the floor. We want to define the error, and we want to minimize the error. And that's the key of most machine learning problems. You take your problem, you define the error, and you minimize it using gradient descent. So going around yourself and figuring out in which direction you decrease the error the most by calculating some derivative. This is how we solve most problems in machine learning. So for example, we teach a computer how to play Go, or we can teach a computer how to play Jeopardy, or a very, very cool application is we can teach a car how to drive itself, or many more. You can teach a computer how to detect spam mail, how to recognize faces in a picture, things of finance applications or medical applications, many applications in general. And at the core of all these applications is this concept that I'm going to teach you today, neural networks, which is the basis of deep learning. So what is the first thing that comes to your mind when you think neural network? I don't know you, but when I first heard neural network, this is the first thing that came to my mind. It was just some robot somewhere with claws and like a brain and some liquid and something scary, futuristic. But luckily, then I started seeing actual neural networks and I realized that they are a lot scarier than that. This is an actual neural network. There are these little nodes all over the place and edges between them and things called layers and hidden layers. It's very ugly. But I've been working with neural networks and trying to understand them for a while, and I finally see them in a different way. This is how I see a neural network. When I think of a neural network, I think of a kid playing in the sand, and there are some red shells and some blue shells. And you tell the kid, okay, can you draw a line to separate those red shells from those blue shells? And that's exactly what the goal of neural networks is you have some data in the form of some red points and some blue points, and you want to tell the computer, hey, can you split the data? So the computer goes, yes, that's what I did. I drew a line, or some more maybe complicated solutions. But the idea is to teach a computer how to split data. And how do we do this? Well, in the same way that we found that cake, or that we descended from the mountain. So let's look at a small example. This is our data. We have 3 blue points and 3 red points, and we're going to teach the computer how to split the data. So like in the cake, we start in some random position, right? The random position is draw a line somewhere. And now I'm going to randomly say the points on top are going to be, I'm going to think they're blue, and the points on the bottom are red. And now how did I do? Like, how good is that solution? Well, we can see that it's not ideal, right? Because it did correctly classify 4 of the points, 2 blue, 2 red, but it mistook 2 of the other points. Like the point at the very left, it thinks it's blue when it's red, and the point at the very right, it thinks it's red when it's actually blue. So we need to find an error function. We need to tell the computer how badly it's doing, like how far is it from the cake, or how far is it from the floor. And it seems like one sensible error function is how many points am I misclassifying, right? Like how many errors do I have? Here I have 2 errors, so I'm cold. So I can do gradient descent and move this line around and to see where I can decrease the error the most, and then maybe I can manage to decrease this error by 1 by classifying correctly 1 point, and then I can do it again, correctly classify the other point, and now I'm hot because I have found my solution, which is 0 errors. So this is almost the correct solution. There's a very, very small subtlety that makes it actually impossible for us to solve this problem with that error function. I'm going to show you what the subtlety is. Here's our problems again. We have the get cake problem, the descent from the mountain problem, and our third problem is split the data. And remember, how did we get the cake? By calculating the distance to the cake and minimizing it. How did we descend from the mountain? By calculating the height and minimizing it. And now we think that we can solve the split data problem by minimizing the number of errors. But now here's a problem. The distance to the cake is a continuous function. So if I move around a little bit in tiny steps, the distance is going to decrease in very, very tiny amounts. As a matter of fact, I can find the derivative, and that's the whole point. The same thing with descending from the mountain. If I move around in tiny, tiny steps, the height decreases in very tiny steps, so I can actually see where I can decrease the most or calculate the gradient. Here, it's not the same thing. With the number of errors, it's actually a discrete function. I can be like, okay, there are 2 errors, and then I move around the line a little bit, and then I still have 2 errors, and I move a little more, and I still have 2 errors, and then all of a sudden it jumps all the way to 1, or it jumps all the way to 3 or to 0. That's called a discrete function. It's continuous, and in particular, I can't find the derivative. And if you remember, the basis of gradient descent is finding a derivative. In the picture, what I'm trying to do is basically use gradient descent to descend from a flight of stairs instead of from a mountain. So I look around myself, and if it's foggy and I can only see my proximity, it almost feels like I'm in a flat land. Like I can't really figure out in which direction I descend the most, so I get confused. So we need an error function that is continuous. So let's try to build it. The way we're going to try to build this function, by the way, this is called logistic regression. So it's an algorithm. The way we're going to build this function is the following. We're going to give every point a penalty. The points that are misclassified, so that red point in the left and the blue point in the right, they get a big penalty because they're wrong. And the points that are correctly classified, they still get a penalty, except a much smaller penalty. So you can see how like the penalty here is how big the point is. And then I add these penalties together, and that's my error function. Okay. And now I can move my line around, which is the equivalent of looking around me and on seeing where it can descend the mountain the most. And we can say, let's move the line to this position. And now I've seen that, yes, I have changed every penalty. Some of them have slightly increased, but the big ones have decreased by a lot. So when I add them, I get a much, much smaller error. So now the point is to minimize this error. And now we can use gradient descent because now the function is continuous. Let's look at a more visual representation of this. So in the left, I'm descending from the mountain. In the right, I'm trying to split my data. And my error function on the right is the sum of the penalties of the points. And on the left is the height. But you can see that I've made it in such a way that it adds to the same thing. Now I move my line around, which is the equivalent of looking around me in the mountain. I pick the direction where I descend the most. I move in that direction. I've managed to decrease my error. Again, I look around in all the directions I can go. I take a step in one direction that decreases the error or the height the most. Now I've been able to decrease my function to a minimum, thus finding my best possible solution. But now I think I left a detail behind, right? I didn't tell you how to build this error function. So now I'm going to tell you how to build it. So let's remember what we're trying to do. We're trying to find a line that splits the data. But actually, I want more than a line. I want a whole probability function. So I want to be able to color every single point in the plane. Points that you see at the top and the very right are very, very blue. They get less and less and less blue as they reach the line. Somewhere in the line is the 50-50 line, so they're like kind of not blue, not red. And then below the line is the red area, and then the very, very bottom bottom right, the area is very, very red. And then the color is the likelihood of the point you're going to find. So if I plot a point somewhere in the top, it's very likely to be blue. If I plot a point somewhere in the bottom right, it's very, very likely to be red. And if I plot a point somewhere close to the 50-50 line, then as it's called 50-50, then the probabilities are 50% that's blue and 50% that is red. So that's a probability function. And how do we build a probability function? Well, let's mark every point in the plane by its blueness. So let's take our favorite line and draw it in the middle as a 0 line. And then let's take some spacing and just translate this line by 1, by 2, by 3, and then by -1, -2, -3. And we've been able to give every point in the plane some number from -infinity to infinity. And that number is the amount of blueness. So a very blue point will get a large number like 27 or 28.5. And a very, very red point is going to get something like -100. And the points that are sort of neutral get something close to 0. But this is not a probability function because a probability function, probabilities go between 0 and 1, and these numbers go between -infinity and infinity, right? What I really want is something like the plane at the right. I want my 0 line to be my sort of 0.5 line, now my 50-50 line. And then as I go up in the blue area, I want numbers to get closer and closer to 1. And as I go down in the red area, I have my numbers closer and closer to 0, because in the red area you're very unlikely to be blue. And whereas in the blue area you're very likely to be blue. So what we're going to use to turn the graph in the left to the graph in the right is we're going to use an activation function. So an activation function is a function that takes your entire number line into the interval 0, 1. So on the top you see the number line, 0 is in the middle, then 1, 2, 3 to the right, and -1, -2, -3, etc. to the left. And every point gets mapped to some point in the interval 0, 1. So for example, the 0 gets mapped to 0.5. The 5 already gets mapped pretty close to 1, 0.99. The -10 gets mapped pretty close to 0, 0.0001. And in general, every point, huge points get mapped to something very close to 1, and huge negative points get mapped to very close to 0, and the numbers around 0 get mapped to numbers around 0.5. I like to see this function in my head as a magnifying glass, because if you look at the entire number line through a magnifying glass, the points at the right and at the left kind of like crunch into the sides, and then the points in the middle kind of stay the same. If you and math are in speaking terms, the formula for this activation function, this is called a sigmoid. It's 1 over 1 plus e to the minus x. You can see that if x is large, this function is very close to 1. If x is small, large negative, this function is very close to 0. And if you are in particular 0, you get 0.5. So what we're going to do is we're going to take our numbering of the points in the left, apply the activation function, and now we get a whole probability function for every point in the plane. Every point in the plane gets assigned a number from 0 to 1, and that number is the probability that a point being at that position is blue. So in particular, the points that are 50-50 to be blue or red are in the line in the middle. And now let's look at these 4 points, and let's try to calculate some probabilities. So let me think of a random solution. This is obviously not that good, but a random line that tries to split the points and that gives them a whole probability distribution. And let's try to figure out how likely is it that these 4 points are of the colors that this probability function says they are. So look at the point in the very top left. That point is red, and it's in a blue area, in a pretty blue area. So the probability of it being blue is 0.1. Then there's this point 0.6 in top right, because it lies in the blue area, but close to the line. So it's more likely to be blue than red. Then there's this point in the bottom left, 0.7. Well, that point is also in the red area, so it's correctly classified, and it's and the probability of being red is it's more than 0.5. And since it's kind of well into the red area, let's just say 0.7. And then at the bottom right, we got the 0.2 point, because it is a blue point living in a red area, so it's very unlikely to be blue. And now, if we think that these are independent events, the probability of all 4 of them happening, it's actually the product of the probabilities. So if I have these 4 points and this line with this probability function, the probability that the points are of those colors is the product of the 4 probabilities, which is 0.0085. So it's not very likely. Now let's move the line around. Now let's look at this arrangement. This arrangement seems a little better. What are the probabilities that these points are of those colors? Well, the 2 points in the left are red and are well into the red area, so let's just say the probabilities are 0.8 and 0.6. And the numbers to the right are blue, colored blue, and then well into the blue area, so the probabilities are 0.7 and 0.9. And so the probability that these 4 points are of those colors is the product of the 4 probabilities. This one gives us 0.3024. Now, that's a lot more likely than the top one, so we can say that it's more likely that the solution is this one than the previous one. This thing what we just did is called the maximum likelihood. Okay, and that's how we're going to calculate our error function. Now, I promised me an error function, a penalty that I can add to each of the points and then add these points to get an error function. And all I've done so far is multiply probability. So let me deliver on my promise. So here are our two arrangements. Here are our two probabilities. This is the probability of the first arrangement happening and the probability of the second arrangement happening. And now, question, how do we turn a product of things into a sum of things? And the answer is we take the logarithm. Now I took the logarithm and I also multiplied it by -1 so that I get positive numbers. I can also do the same thing at the right. I take the logarithm. Now at the left, I get minus the logarithm of 0.0084, which is around 4.8. At the right, I get minus logarithm of 0.3024, which is 1.2. And in general, the higher the probability, the smaller the negative logarithm of it is. So now we have a genuine error function, and to each point we can assign the corresponding logarithm, negative logarithm of the probability, and that's gonna be the error function that we assign to every point. That's gonna be the penalty. And as you can see, this is, if we add them, we get the total error. For example, look at this point. It's pretty badly misrepresented because it is a red point well into the blue area. Its penalty is 2.3, which is negative logarithm of 0.1. This same point on the right is well represented because now it's a red point in the red area. Its penalty is minus logarithm of 0.8, which is 0.2. So now I finally delivered on my promise, which was an error function, a penalty on every point that tells me how badly misclassified is this point. And when I add them, I get my error function. And the algorithm of defining the error function this way and solving the problem using gradient descent is called logistic regression. Now, why are they called neural networks? Well, we'll get there, but here's a little visual representation. Look at this line that splits the red points and the blue points, and its equation, like an equation of a line. Let's say it's 2x plus 7y equals 4. And the blue points are the points in the plane where 2x plus 7y is bigger than 4, and the red points are the points where 2x plus 7y is smaller than 4. So we're going to represent that as this little node here, where the inputs are the x and the y are two coordinates, and the 2, the 7, and the 4 get located in the two edges and in the central node. So you can see that like the 2 times x is the 2 in the edge times the x in the node, and the same thing with the 7y, and then the constant, which is the 4, is in the middle node. And this is called a neural network because that kind of resembles a neuron. On the left, you have the two entering points, which are x, y, and what this does is it checks if the point x, y is in the blue area or in the red area, so in the positive or negative area. It calculates the probability that the point is blue, and then it just throws out that 0.9. In the brain, we have the neurons that take, on the dendrites, take as input a bunch of nervous impulses, and then from the axon throws out another nervous impulse. So this is sort of the analogy that's happening here. And in the same way that in the brain you have many neurons, and the inputs coming out as the output of a neuron becomes the input of another neuron. In the same thing, in the same way in a neural network, we're going to have a bunch of little nodes like the one on the left, and the outputs of a certain node is going to come in as the input of another node. But we'll see it more carefully in a minute. So now let's make things a little more complicated. Let's say our data looks like this, the red points and the blue points. And now we want to split it. But now we can't really use a line because this data is not linearly separable. So what's the next thing after a line? Well, we can use this kind of curve like this, right? This curve correctly splits the data. But now the question is, how do we get curves? I mean, well, let's use what we have. We know how to construct lines. So what we're gonna do is we're gonna take, for example, the line in the top, which is an okay solution, and the line on the bottom, which is also an okay solution, and somehow we're gonna try to merge them to get a perfect solution. And the merging of these two lines, we can see that the top right region is blue, and it kind of resembles this. So we're going to learn how to take the two regions on the left and make it into the region on the right. In other words, what we're going to think of it is like arithmetic, right? You take two regions and you add them to get a third region. In this case, we get the two linear regions, and we add them to get this curved region on the right. So let's see how we can do to add two regions. Let's pick a random point. So let's pick this point. So by the model in the top, this point has probability of being blue of 0.7. Now we take the same point on the bottom, and the probability of being blue, let's say it's 0.8. So what would be the way to add these two? Well, we can think of it as just adding the probabilities. So in our sum, the probability of this point is 0.7 plus 0.8, which is 1.5. But now we run into the same problem as before. 1.5 is not a probability. Probabilities have to be between 0 and 1. But if we remember correctly, the last time we had to deal with this, we used the activation function. So all we do is we use the activation function and turn this 1.5 into a 0.82. So in summary, what we did to add the two regions on the left to obtain the one on the right is take the probability that's given at every point, add it to the probability at the same point in the bottom region, and now to that sum we apply the activation function. Now, what happens if I want to combine two regions, but I want the one in the top to have more of a say? So I want a weighted combination where the area in the top has a higher weight. And then the area would look like this, where the bottom area is just less powerful, and then the sum of areas looks more like this, which looks a lot more like the top region than like the bottom region. Well, the way to solve this is by just saying, I'm going to take my favorite number, 7, and instead of considering the sum of the two areas, I'm going to say 7 times the first area plus the second area, and that looks a lot more like the first area than the second area. I can even put the weights that I want. I can say 7 times the first area plus 5 times the second area. And the way I do this is, again, by calculating the probabilities at each point. And now, in the resulting point, I take the linear combination, 7 times the top probability plus 5 times the bottom probability. And now let's just say I put a random number here, because linear combinations can also have constants. So I subtract my number, 6, and then I can get 2.9. So I can find a linear combination of the two areas, including a constant if I want. And the way to get this area is by just applying the activation function. So now I'm going to encode the linear combination of the two areas with the coefficients 7, 5, and minus 6 as this node, where in my edges I have 7 and a 5, and in the third node I have minus 6. And now it seems like we can build our neural network in the following way. Here I have my one area, where the equation of the line is, for example, 5x minus 2y equals minus 8. I encode this as this neuron in this way I showed you before. Then I have my second area, where the equation of the line is 7x minus 3y equals 1, and I encode that as this neuron. So let me draw them here again and again. And now, if I combine these two areas with coefficients 7, 5, and minus 6, I get this area on the right. And now the magic happens here. I put these together, and I get my neural network. I can clean it up a bit, and now when I get the neural network on the left with inputs x, y, and as coefficients all these numbers in the edges and inside the nodes, what I'm really thinking is that on the right I am having one area and another area and combining them to get that curve on the right. So if you're going to remember one thing from today's video, remember this. Whenever you see a neural network like the one on the left, think of it as some combination of areas like the one in the right. And so this is the mental picture I have when I see a neural network. I have my input layer, which is the x and the y. This is the coordinates. My hidden layer is the lines that I'm using to cut up my final region, and the output layer is the final region that I obtain as a combination of those linear regions. Now I can play with this input, hidden, and output layers as much as I want. For example, I can make the hidden layer bigger. Let's say my area looks like the one on the right. So now I need this area to look like the combination of 3 lines instead of 2 lines. That's no problem. My hidden layer now has 3 elements, and by adding linear combinations of these 3 lines, I get my sort of triangle at the right. What happens if my input layer is larger? If instead of having 2 inputs, I have 3 inputs, that means instead of being in the plane with x and y coordinates, I am in space with x, y, and z coordinates. And now, instead of lines that cut the plane in two, I have planes that cut the 3D space in two. And in the same way as before, I can combine these regions in order to get a region like in the output layer. And I can also do probably the most important of this, which is I can add more than one hidden layer. In this example, I have 2 hidden layers. So my first hidden layer draws a bunch of lines through my data. My second hidden layer combines these lines to make some more complicated regions. And then my third layer, my output layer, just combines the elements from the last hidden layer to make a much more complicated region. So you can imagine how if I have many hidden layers, I can create the most complicated regions I want. And this is the definition of a deep neural network. A deep neural network is just a neural network with many hidden layers. Here's an example. This is the deep neural network used to play Go. So the input is the board. It has 5 hidden layers and then an output which tells you what to do in the game. Here's another example. It's a neural network for the self-driving car. So the input is given by the pixels in an image. And then as it goes through a hidden layer. Actually, the real one has many more hidden layers, but this is just a simple example. And the output comes out with a answer of turn left, turn right, go forward, or reverse. And that's it. That's the definition of a neural network and deep learning. So thank you for sticking all the way to the end. I hope you enjoyed it. If you like it, feel free to subscribe or like or share or comment. I'm very happy to see comments. I'm very happy to see suggestions on what other topics you'd like to see, or how could I make this better, or any questions you have. You can also email me or find me on LinkedIn or find me on Twitter. And if you like what you saw, you can see more of these classes at Udacity where I teach. Thank you very much. Bye bye.